Hello and welcome to the channel. This video aims to explain the terms exponential growth, R rate and herd immunity. These are bandied around daily in the media by journalists and politicians, many of whom have no proper understanding of what they actually mean or imply. Let's take exponential growth first and have a look at this graph. The three lines all start off at 100 units. The blue straight line represents linear growth, where the quantity grows by a fixed amount each time period. In this particular example, it's 20 units. Thus, the quantity grows from 100 to 300 over the 10 time periods. An example may be the stock level of an item if 20 units are bought per day with no usage. The growth here is not dependent on the existing stock level. Let's now turn to the orange and red lines, which show the number of units growing exponentially by 30% and 100% respectively, or by multiples of 1.3 and 2 of the current quantity each time period. Thus, as the quantity increases, so does the growth, because an ever-increasing number is being multiplied by 1.3 or 2. The essence of exponential growth is that the rate of growth is proportional to the size of the quantity in question, and as the quantity increases, so does the rate. The quantity in each period is a constant multiple or a proportion of the previous one. There are many natural processes that exhibit this behaviour, with examples including early population growth, such as in a new colony of rabbits. As the population grows, so does the number of newly born. Exponential growth is also exhibited by bacteria and by contagious diseases such as COVID. If the interest earned on an investment is reinvested, then the capital grows exponentially, because new interest is earned on an ever-increasing quantity. Although I will be uploading a separate video describing some of the mathematics of exponential functions, it's worth just quickly showing that in exponential growth the quantity n at time t is equal to n0, the initial value, multiplied by a growth factor r raised to the power t. Thus for the orange line, the quantity n at time period 5 is the initial 100 units multiplied by 1.3 to the power 5, or 371. We have, in essence, multiplied the initial value of 100 by 1.3 5 times in succession. In maths, a power is also known as an exponent, hence the phrase exponential growth, because the growth is dependent on the value of an exponent. Whilst the term exponential growth is used a lot, it's easy to forget there is also exponential decay, where a quantity declines by a constant multiple each time period. Here we have a graph comparing linear and exponential decays. The straight blue line starts at 100 units and declines by 5 units per time period. An example may be how the stock level of an item reduces if you use 5 per day. The orange and red lines show exponential decay, where the quantity reduces by 20% and 50% respectively each time period, or by a multiple of 0.8 and 0.5. This is the mirror image of exponential growth, in that the decay rate gets increasingly smaller as the quantity reduces, because the rate is proportional to the quantity. There are numerous natural processes that exhibit this behaviour, with examples including radioactive decay, the rate of heat loss from a hot object, say a cup of tea, where the rate is high initially then tails off. The reduction in infections from COVID following interventions such as lockdowns would also exhibit this trend. Exponential growth should become even clearer on this slide, where we discuss the R rate. The R rate is a measure of how easily a virus spreads, and is simply the average number of new infections that are caused by one infected person. When a contagious disease is initially spreading in an uncontrolled way, with no interventions, the R rate is called R0, the basic or natural reproduction number, in the environment it's in. When interventions such as social distancing are put in place, the virus will transmit at a lower but varying rate, and this is called RT, or simply R, the time-dependent R rate. This is the R rate that the media refer to daily. For the variant of COVID-19 that took hold in Europe in February 2020, R0 was around 3. Thus one person infected 3 others, who in turn each infected 3 more, and so on. After only 5 generations or time periods, we end up with 243 infections. This is high exponential growth, because the number in each time period is a multiple of 3 times the previous one. The generation time period is related to incubation period, and is generally taken to be 5 days for COVID. Thus in 5 generations of 25 days, the virus has multiplied by a factor of 243. Although the R rate is used in mathematical modelling of epidemics, it's not easy to get a feel of what it actually means in practice, even for experts. That's why it's sometimes better for presentational purposes in the media to describe an epidemic in terms of doubling time, or the time taken for cases to double. For example, an R rate of 3 leads to doubling in around 3 days. We can see that the number of cases are given by 3 raised to a power, or exponent, which increases with time. Because of this exponent dependency, growth can mushroom quickly. Have a look at this example where R0 is 6, as is likely the case for the Delta strain of COVID. The emerging Omicron variant appears to spread even more quickly. While this rate may only appear to be 2 times the original R of 3, this is only true at generation 1. This initial ratio of 2 also grows exponentially with time, and after only 3 generations the ratio is 8, hence why we have 216 cases versus the original 27. Let's move on to looking at how real data can indicate exponential growth. Here we have a plot of known COVID cases up to the first UK lockdown on 23rd of March 2020. The data are indicative of exponential growth because the gradient or rate of growth keeps increasing, and also because we can detect an approximate doubling time from them. If the data are plotting on a logarithmic scale, then an approximate straight line indicates exponential growth. This is because a log scale shows proportional change, not linear change, and hence a straight line on it indicates that cases grow by a constant proportion or multiple each time period. The doubling time derived from this plot is around 3 days. It should be noted that because of the limited testing available in this period, actual cases are estimated to have been 50 to 100 times greater than those shown in the graphs, with probably over 1 million people having been infected by the first lockdown. The limited testing coupled with the rapid doubling time hindered decision making at the time. Things would have been far worse had the Delta variant been the original variant. With its R0 of around 6, it may have led to around 20 times more cases by the 23rd of March, as shown on this graph. However, it should be noted that lockdown would have occurred a week to 10 days earlier in this event, as cases would have grown more rapidly. Let's now move on to discuss herd immunity. Herd immunity occurs when a large proportion of a community, the herd, becomes immune to a disease, making the spread of disease from person to person unlikely. As a result, the whole community becomes protected, not just those who are immune. Here we have a virus such as the Delta variant with an R0 of 6, and it spreads exponentially in the early stages through a population that is fully susceptible. After some period of time, far less of the population remains susceptible, either through natural immunity acquired from previous infection or from vaccination. When we reach a stage where 5 out of 6 or 83% of people can no longer become infected, then we have reached a stable phase where one infection only leads to one new one. The R rate is equal to 1 and the disease no longer grows. This point is known as the herd immunity threshold. When the herd immunity threshold is exceeded, with more than 5 out of 6 people immune, then we have a phase where R is below 1, and the spread of the disease declines to very low levels. The more contagious a disease is, the greater the proportion of the population that needs to be immune to it in order to stop its spread. For example, measles has an average R0 of around 15, which means that more than 14 out of 15 or 93% of people need to be immune. In this table we compare the basic R0 and herd immunity thresholds for common diseases. It can be seen that measles is top of the list, but chickenpox and mumps are also highly contagious illnesses. It's estimated that over 92% of the population must be immune to interrupt their chain of transmission. Herd immunity for diseases like measles, mumps, rubella and polio has been successfully achieved by vaccinating a very large proportion of children at a relatively young age. Chickenpox, it has been achieved by natural infection. Smallpox is a unique case, as it's the only disease that has been totally eradicated from the human population through mass global vaccination. As to COVID-19, the current variants are highly contagious, much more so than, say, the seasonal flu. The achievement of herd immunity may be difficult because, unlike the other diseases mentioned earlier, vaccines do not fully stop transmission, infections do not confer long-term immunity, and mutations have not stabilised. However, on a more positive ending, While COVID will not be eradicated, it is likely to become endemic over time, meaning that it will continue to circulate in relatively stable numbers in sections of the global population and cause outbreaks in regions where cases had been low. That concludes this video. I'm uploading 3 other related videos, one to do with the mathematics of exponential functions and 2 lighter ones for general audiences, which show 2 interesting simple problems highlighting the power of exponential growth. Thanks for watching. Please subscribe to see more like this, and I will see you in the next one.